So I'd like to explain how to analyze the long-term pumping test. What we did initially was to take the data that you measured during the test and put it into Excel and then do a few simple manipulations to get it into a form that can be analyzed. So the data are here. This is the time that you measured. Here's your name. And the depth of water that you measured is here. And the actual time that you measured is there. Okay, so that's the data that you wrote down in the data sheet. And what we wanted to do is get that into the form of drawdown as a function of elapsed time. So it's fairly straightforward, but it took a little bit of doing. Here's the days in elapsed time, and the calculation required. This ends up being, this ends up being just in a format of time here, and it works okay up until the next day, up until Saturday. And so we had to go and turn this into days, into decimal days. That really just involves changing the format. But the thing that was important to do once you switched from Friday to Saturday was to add in the elapsed time in days that happened on Saturday. So see, there's 6 a.m. and the elapsed time is 6 hours and 8 minutes plus however much time there was on Saturday. So it turns out that's 0.23 days. So right here under the elapsed days column, it's given here. It's given as the day, or the time here, plus the 0.23 elapsed days from the previous day. Okay, so that works for Saturday. And then for Sunday, we just had to do the same thing, except we had to add 1.23. So for the 6 o'clock reading on Sunday, that's given here in elapsed time, and that's the 6 hours and 23 minutes converted into decimal days, and you do that just by changing the format in the column, and then adding to it 1.23 days, which is the number of days from midnight on Sunday to the time the test started on Friday. Okay, so that's how we got the elapsed time in days, and then we converted that to minutes. And then this is the observed drawdown, which you've calculated now by hand, and it's just the depth to water minus the initial depth to water. And then we had to do the seasonal trend. So we needed to remove the seasonal trend, and I assumed that the seasonal trend was linear. I'll show you how I did that in just a sec. And here's the seasonal trend. This is the amount of drawdown. As it turns out, the water level is dropping, and so seasonally, and so because it's dropping, there's apparent drawdown that would occur as a result just of the seasonal trend. And so this is the amount that would happen right here, 0.07 feet by the end of the test. And then this column here is the observed drawdown that's corrected for the seasonal trend. And we do that, the calculation is shown up here, and that's the observed drawdown minus the seasonal trend. And what you can see, I think, is that these numbers are pretty similar. This is the observed drawdown, 49.38, and the corrected is 49.34. So they're pretty similar. So this is the pumping well, and then well, actually, let's then scroll down here. Oops. We also want to do recovery. So first I calculated T prime, and this is the time since the pump was shut off. And so I did that by, this is the elapsed time here in minutes. And so I went over here, and this is the time since the pump was shut off. That's when the pump was shut off. So This is just the elapsed time since the pump was shut off. And let's see, I can show you how that was done. So that's that time minus that time. And we always subtract off that time and just copy this down, the cell reference. And then right here, this is the ratio of this time. This is t, and this is t prime. And so this is that calculation that gives you the time that you would plot for the recovery. And the drawdown that we were interested in during recovery is right here. Okay? And that's just calculated from your data. So this is really just your data, the stuff that you measured in the field, and I've just fiddled around with it a little bit in Excel to make it easier to plot and analyze. And so we did the same thing for the monitoring wells. Here's LAR2, and we've got actual time and depth of water. We did the conversion to days, then to minutes, then we calculated drawdown, and then here's the corrected drawdown, and then in these columns down at the bottom is the recovery. Another thing that we did is to we're going to plot the drawdown as a function of time divided by r squared, and this was described in one of the videos. So we just calculated another time scale, and if we click on this, you see that it's that's the cell reference for the time. Let's see, that would be right there, and then that is the cell reference for the radial distance, and it's squared. Okay, so that'll give us this column, and we'll just make a plot that uses this as the time scale, or as the x-axis. Yeah, right there is the radial distance in feet for LAR2. That's the radial distance away from the pumping well. Okay, so that's the data set. What I did was to do this for all the wells, and then compile the data and plot it up. And I made the plots and I put them in PowerPoint, and so I'm going to switch over to PowerPoint and take a look at them. So here's the PowerPoint. This is what we've got. I'm going to show you about the background trend, how to do the background correction, drawdown in the rock wells, recovery in the rock wells, and then the saprolite and LBR. There was a little bit of a signal there, and we'll take a look at that, and then the pumping well. Okay, so we had a pressure transducer in the monitoring well LAS1, and that's been there for a couple of years actually. And so it measures the total pressure, which is the water pressure above the transducer and the barometric pressure. And so here's the signal in pascals. And from, well, there's February 20th, so this is sometime around the end of February, and this is May 7th. This is right before field camp. So you can see that it's kind of bouncing around. The units are in pascals, or actually, I'm sorry, it should be kilopascals. This is in kilopascals, and so 1 kilopascal is equal to 10 centimeters of water. So we can figure out how much water this would be. I guess it would be, multiply by 10, and that's how many centimeters. So 1,230 centimeters. So that would be equivalent to 12 meters of water. But there's about 10 meters of water from the atmospheric pressure. So this is the total pressure, remember. Okay, so what you see is it's kind of bouncing around. You see somewhat of a trend here the last few weeks, but not too much of a trend here. But it does seem to be going up and down a bit. And then the other thing that I should point out is see how you have pretty much of a clean line here, but here you have kind of a jagged line. So the sensor is becoming noisy here, right here at the end, the last few weeks. And the noise in the sensor, it's not entirely clear what's causing that, but that's not a good thing. That's an indication that there's something wrong with the sensor. So what I'm talking about is the signal right in here, and it's kind of, the signal is kind of going like that. And so probably one possibility is that the battery is getting low on that sensor. But this is the kind of really clean signal that we want to have with this kind of sensor. Okay, so this is the total pressure, and what we need to do is have the, let me see. Okay, here's what I want. So we want to have the barometric pressure and subtract off the barometric pressure from the total pressure. So this is the plot that I just showed you. The scale is now different. This is a much bigger Y scale. And this is the barometric pressure. So let's see, this is 100 kilopascals. So this is barometric pressure. It's about 10 meters of water equivalent. And this should be 120. I guess the ones here got cut off, so that's 120 and so on. And so this is about 25 kilopascals greater than barometric. And the reason for that is because the transducer in the well is 2.5 meters roughly below the water level. So there's so this is the static water level above the transducer. Okay, so that's what's going on. And then the other thing that you should take a look at is see the major features in the actually the major features in both of the let me turn this thing off. Let me erase these. So the major features in both of these curves are similar. So see how this kind of has a little pointy place that drops down. That one does the same thing. And then this one has a little cusp that goes up. That one does the same thing. And then it goes down, and there's a little point. It goes down, and there's a little point. So these signals look really quite similar. And indeed, the signals are, this signal has this signal in it. Okay, so what we do is subtract these two, and then I'm going to subtract them. I'm going to multiply by 10 to get centimeters of water, and then I'm going to start it off at 0. So if I do that, I get this. This is the signal up here, and so it's in centimeters of water. I started it off at 0. Actually, I set it up so that it would start at 0 right at that point. And what you see is, well, it's kind of bouncing around. It drops, it rises, and then notice this trend here. So this is March 20th here. So right about spring break, and we start to see it's dropping at a fairly uniform slope. The signal is going up and down, and that's just noise in the transducer. Here it's a bit less, actually a good bit less, and now the noise has increased, but that's probably not a real signal. It's probably just a noise in the sensor. But we have a linear decrease, a linear trend, and then we have this big jump. And so this is April 4th, and I didn't check, but I would be willing to bet that there's a rainfall, probably a big rain, on April 4th, and the water level rose by, here it's starting at -5, by, it looks like about 10 centimeters. So it rises by 10 centimeters in a day or two, and then it's up elevated here. Okay, and then let's see, here's April, excuse me, April 17th. And shortly thereafter, late April, it starts to decrease, starts to fall, and you can see it's noisy now, but it's falling in roughly a linear trend. Okay, so what and this is right at the beginning of field camp. So I went and fit lines to these, and this line here is about ½ centimeter a day, and this line here is over 1 centimeter a day drop of the water level. And so this is fairly typical, this rate, a few millimeters, 5 millimeters a day. This is quite large, and what I think is happening is that this is probably the typical seasonal drop in the water level, but there was this influx of water right here as a recharge event that raised the water level higher than it would have been typically, and because it was higher, it flowed out faster, and so this drop in the water level is because the water had come in and recharged the system, and that led to this more rapid decrease. So in any case, regardless of why it's occurring, the information we have looks like we have about this rate of drop. I should point out too that this signal here, let me go and turn off the writing. And so this signal, let's look up here. This is what the water level is doing. If we just compare that to this signal, this is the pressure from the transducer. And you can see here the water level is dropping, but this part of the signal looks quite different than it does here. And that's because this signal here is the difference between the signal that we measured in the well and the barometric. And those two signals are pretty similar to one another, and it's only when we subtract them that we see actually what looks to be a fairly different appearing signal. So it's important when you use this kind of transducer to have both a barometric transducer and a submersible transducer. Okay, so this will give us what we want, a regional or a seasonal trend, and we'll just assume that the water level is doing that throughout our test. Okay, so let's take a look at the data from LAR2. This is during the test, and this is elapsed time and the drawdown. So I plotted the observed data here in the blue line, and I plotted the trend, the seasonal trend there in the orange line. And I mean, you can see that the seasonal trend shows up on the plot, but it's just showing up as a very small amount compared to the observed trend at LAR2. When I subtracted them, I got this red line, and you know, you can see over here, you can see the difference, but the difference is quite small, and this amount of difference for this particular test won't really affect our interpretation. So this is how you do the seasonal trend and how you make the correction for it, but it's not going to affect our results in this case. But this is something that's important for you to know how to do, because in other cases, in other tests, it may end up having a rather important effect. So you may need it down the road. So here are the data from the 6 monitoring wells plotted all on the same axes. We see drawdown as a function of time, and the legend over here describes which one of the monitoring wells the results are from. We can see that a lot of these plots are really quite similar. These are the 4 rock wells in addition to the pumping well, and they give a signal that's really remarkably similar. And then here, this is LAR, that's LAR, LAS1, the saprolite well, and the circles here are LBR, the well that was down the hill. So what we see is that we've got the slope is flat at first, and then it curves up. This is a semi-log plot. And then we've got a portion in here that's roughly semi-log straight line. So up to this point, up to about 100 minutes, or maybe a little bit beyond, say up to about that point, the data are really what we expect from the Jacob analysis. It goes on the semi-log straight line, and we can do the Jacob analysis. But then we have a much different response, and it really happens quite suddenly. I think that it probably is starting to kick in right towards the end of Friday night. These data here are the last data on Friday night, and then this is the wee hours of Friday. And so during those wee hours, the wells change behavior by quite a lot. And what happens is the slope of this drawdown plot, drawdown as a function of time, flattens out really a lot. And out here, really for the rest of the test, there's a little bit of increase in drawdown, but not really much. Essentially this is just going to flat. Once we started measuring Saturday morning, the drawdown was essentially the same for about a day, from Saturday morning till Sunday at midday. And then we shut off the pumps right here, and it drops suddenly. Now keep in mind this is a log scale, so that distorts the time. It really amplifies this early time period and compresses the late time period. So we have part of this test that really is similar to the Jacob analysis that we've been expecting, but the later part of the test is really much different. And the way we interpret this is that the early part, really before this line, is the well is removing water from storage, and it's behaving much like a aquifer of infinite extent. And so that can be analyzed by the Jacob analysis or the Tice analysis, and we get some pretty good results. But then at about this time something happens, and this idealized case that the aquifer is of infinite lateral extent really starts to fall apart. And it has to. We can't have an aquifer of infinite extent. And so what we think is at about this time, at about 200 minutes or so, the aquifer starts to interact with the stream. And instead of pulling water out of storage, then it can capture water that either is coming out of the stream or that would be headed towards the stream as recharge. So there's an interaction with the stream that provides water to the well that does not require that water coming out of storage. And as a result of that, the pressure doesn't have to drop. We can get water from the stream instead of dropping the pressure and pulling it out of storage. And so that's why these curves all flatten out. And then when we shut off and it goes on recovery, we get a response like we see here, and we can't really see the scale is wrong to see the response for recovery here. But with this conceptual model, we should have some response during recovery that is affected by the formation properties. So that's the interpretation. What it means is that we can analyze the early part of the test using the methods that we've seen so far, and this later part of the test we analyze using a different model. Now there are many different models that are used to analyze pumping tests. The Jacob or Tice analysis is really among the most simple, but there are dozens more, and they're available. Some of them, anyway, are available in software, and there's actually quite a nice software package that is called Octasolve. What is it? To solve something like that. That has many of these solutions. So for those of you who are interested in looking into this more, you could take a look at Octasolve. You can download Octasolve and get a demo version that has a lot of functionality. So what I want to do here is analyze this and really check out two things. I want to go and analyze it using the Jacob analysis because we see that part of this analysis is behaving the way we expect the Jacob analysis to. And then what's happening here is the drawdown is flattening out, and we're interpreting that to be an interaction with this stream. And that means that this system is going to steady state. That's what is implied here. And so what we're getting is a system that's headed to and getting pretty close to, at least it looks like, a steady drawdown. Okay, and so we could think of this as going to a steady specific capacity, where we take the drawdown, we take the flow rate divided by the drawdown and calculate the specific capacity. So I want to try calculating the specific capacity. I want to try measuring the specific capacity from the well, and then also try calculating it using the method that's described in the worksheet.